delving into the mysteries of the cosmos. One of the most captivating questions is what caused the Big Bang? And what, if anything, existed before it? This question touches on the very origins of our universe, a topic that has puzzled and intrigued scientists and philosophers alike for centuries. The Big Bang theory, widely accepted among the scientific community, posits that the universe began as a singular, infinitely dense and hot point, approximately 13.8 billion years ago. This singularity, which contained all the mass and space-time of the universe, suddenly began expanding. This expansion is not merely the movement of objects in space, but rather the expansion of space itself. As space expands, it carries galaxies with it, like dots on a balloon that is being inflated. Addressing what caused the Big Bang is a challenge, as our current understanding of physics breaks down when applied to the state of singularity. The laws of physics, as we know them, cannot describe such a high-energy state where all forces of nature are unified. Some scientists hypothesize that quantum fluctuations in a tiny, compact space could have led to the rapid expansion characteristic of the Big Bang. Others propose models involving the multiverse, where our universe is just one bubble in a frothy sea of universe bubbles. The mystery of what, if anything, existed before the Big Bang remains an open and profoundly intriguing question that continues to inspire scientific inquiry and philosophical contemplation. Following the cataclysmic event of the Big Bang, the universe transitioned through a series of remarkable epochs that laid the groundwork for the formation of the first stars and galaxies. Initially, the universe was an incredibly hot and dense plasma of particles, protons, neutrons, electrons, and photons, without any stable atomic structures. This period, known as the Cosmic Dark Ages, lasted for several 100 million years. As the universe expanded, it cooled down, allowing protons and electrons to combine and form neutral hydrogen atoms, a process called recombination. This event decoupled light from matter, leading to the release of the cosmic microwave background, CMB radiation, a faint glow that still pervades the universe today. With the formation of neutral atoms, the universe became transparent, allowing gravity to begin its gradual work of pulling matter together. Tiny fluctuations in the density of matter, imprinted during the inflationary epoch shortly after the Big Bang, began to grow under the influence of gravity. Regions with slightly higher densities attracted more matter, creating the seeds for the formation of structures. Over time, these overdense regions collapsed to form the first clumps of matter. Within these clumps, gas, primarily hydrogen and helium, began to fall into gravitational potential wells, leading to the formation of dense, cold clouds. Inside these clouds, the gas cooled and condensed, triggering the process of star formation. The first stars, known as population 3 stars, were likely massive and short-lived. They were composed almost entirely of hydrogen and helium, as the heavier elements, metals, had not yet been forged. These massive stars burned their nuclear fuel rapidly, ending their lives in spectacular supernova explosions. These explosions enriched the surrounding gas with heavier elements, setting the stage for the formation of subsequent generations of stars and the eventual complex chemistry necessary for planet formation and life. As these early stars congregated, they began to form the first proto-galaxies. The gravitational attraction between these stars and dark matter, which constituted a significant portion of the mass in the universe, facilitated the assembly of larger structures. Small proto-galaxies merged over time to build more massive galaxies, a process known as hierarchical clustering. This framework of structures evolved into the galactic and intergalactic networks we observe today. Modern telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, are crucial in unveiling the mysteries of this epoch. They provide snapshots of young galaxies and early star formations, allowing astronomers to piece together this cosmic history.
By studying distant, ancient galaxies, scientists can observe the universe as it was billions of years ago, enabling them to explore these formative stages directly. The formation of the first stars and galaxies marks a significant chapter in cosmic history, transforming a homogeneous sea of gas into a universe replete with complex structures, leading ultimately to environments where life could potentially arise. These early processes set the stage for the rich tapestry of astronomical phenomena that we continue to study and explore today. The cosmic microwave background (CMB) radiation is one of the most profound and enlightening discoveries in cosmology, acting as a relic from the early universe. Detected in 1965 by Arno Penzias and Robert Wilson, the CMB is the faint glow of radiation that permeates the entire universe, a remnant from about 380,000 years after the Big Bang. This was the time when the universe cooled sufficiently for protons and electrons to combine into neutral hydrogen atoms, a process known as recombination, allowing photons to travel freely for the first time. These ancient photons have stretched into the microwave part of the electromagnetic spectrum due to the expansion of the universe, creating a uniform background radiation detectable in every direction. Far from being just a faint afterglow, the CMB holds a wealth of information about the early universe's structure and composition. Tiny variations in the temperature of the CMB, known as anisotropies, encode crucial data about the density fluctuations in the early universe, which eventually led to the formation of galaxies and large-scale cosmic structures. Detailed maps of these anisotropies, such as those produced by the Wilkinson Microwave Anisotropy Probe WMAP and the Planck satellite, have provided insights into fundamental cosmological parameters. These include the age of the universe, its composition and the rate of its expansion, known as the Hubble constant. Moreover, the CMB offers strong evidence for the theory of inflation, a rapid expansion of the universe immediately following the Big Bang. The tiny quantum fluctuations that existed during inflation were magnified to macroscopic scales and eventually seeded the formation of galaxies and large-scale structures. The CMB's uniformity on large scales, along with its slight anisotropies on smaller scales, supports this inflationary model, constraining the physics of the early universe with high precision. Polarization patterns in the CMB also provide significant clues. These patterns can be divided into E modes, which have been measured with high accuracy, and B modes, which are more elusive and could offer evidence of primordial gravitational waves, ripples in space-time generated during the inflationary epoch. Detecting these B-mode patterns would not only confirm inflation, but also offer insights into the energy scales of fundamental physics, potentially linking cosmology with high-energy particle physics. In addition to cosmological insights, the CMB helps test the standard model of cosmology, known as the lambda cold dark matter. By comparing predictions from the LCDM model with CMB observations, scientists can verify the consistency of our understanding of dark matter, dark energy, and the overall geometry of the universe. Any deviations could point to new physics beyond our current theories, setting a path for future discoveries. The CMB, therefore, is like a cosmic blueprint, offering a glimpse back to the infant universe and answering some of the deepest questions about its origin, structure, and researchers continue to study this primordial radiation, extracting increasingly refined data and thereby unraveling the universe's early secrets with each new observation. Inflation theory is a compelling hypothesis that aims to fill in crucial gaps in our understanding of the universe's infancy, proposing that the universe underwent an extraordinary rapid expansion during the very first moments after the Big Bang. Introduced in the early 1980s by physicist Alan Guth and subsequently refined by others, inflation posits that in a fraction of a second from approximately 10 and after seconds after the Big Bang, the universe expanded exponentially, increasing in size by a factor of at least. This marked an expansion at a rate far exceeding the speed of light, driven by a high-energy field known as the inflaton field. Inflation theory addresses several perplexing issues that were not explained convincingly by the original Big Bang theory alone. One of the primary problems it solves is the horizon problem. Observations of the CMB radiation reveal that regions of the universe, separated by vast distances, have very similar temperatures and properties, suggesting they were once in thermal equilibrium. However, without inflation, these regions would have been causally disconnected since the time of the Big Bang, making their uniformity inexplicable. Inflation solves this by proposing that these regions were indeed in close contact before the rapid expansion, thus allowing for the even distribution of energy and temperature. Another significant puzzle inflation addresses is the flatness problem. The observable universe appears to be remarkably flat on large scales, meaning the geometry of space is close to Euclidean.
These interactions can lead to phenomena like rapid star formation surges, galactic merges, and even the ejection of stars from the galactic center at extraordinary speeds. As we delve deeper into the universe's mysteries, the intricate dance between supermassive black holes and their host galaxies continues to reveal itself as a cornerstone in our understanding of cosmic evolution. Cosmic voids are vast, empty regions in the universe that are almost completely devoid of matter, including galaxies, stars, and gas. These immense voids can span tens to hundreds of millions of light-years across, making them some of the largest structures in the cosmos. In contrast to the densely packed clusters and superclusters of galaxies, cosmic voids are like the dark, quiet spaces between bustling cities. The formation of these voids can be traced back to the early moments after the Big Bang during the epoch of cosmic inflation. In this period, tiny quantum fluctuations in the density of the primordial universe were rapidly expanded, seeding the initial uneven distribution of matter. As the universe evolved, regions with slightly higher densities began to gravitationally attract more matter, growing into the galaxies and clusters we see today. Conversely, areas with slightly lower densities were left with progressively less matter as material gravitated toward the denser region. Over billions of years, this gravitational tug-of-war sculpted the universe into a cosmic web of dense filaments and clusters interspersed with vast, empty voids. Cosmic voids offer unique opportunities for astronomers studying dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are relatively empty and less cluttered by luminous matter, they provide clearer insights into the large-scale structure of the cosmos and the underlying gravitational framework. By mapping and analyzing these colossal empty spaces, scientists continue to unravel the story of the universe's formation and evolution, offering glimpses into the mysterious forces that shape our cosmic landscape. Galaxies interact and merge in a grand cosmic ballet dictated by the inexorable pull of gravity. When two galaxies approach each other, their mutual gravitational attraction can set them on a slow, centuries-long collision course. Initially, this interaction manifests as tidal forces, which distort and stretch the galaxies, creating dramatic tidal tales of stars and gas that can extend for thousands of light-years. As the galaxies draw closer, their interstellar gas clouds begin to collide and compress, often leading to bursts of intense star formation, known as starbursts. These periods of prolific star creation can light up the galaxies, transforming them into dazzling stellar nurseries. As the merger progresses, the galaxy's central supermassive black holes may also converge, potentially merging to form an even more massive black hole. The final stages of a galactic merger are incredibly chaotic, with stars being flung into new orbits and the shapes of the galaxies becoming increasingly distorted until they eventually coalesce into a single new galaxy. This newly formed galaxy typically has a different morphology, often ending up as a more massive elliptical galaxy, rather than retaining the spiral structures that might have been present before the merge. The consequences of such mergers are far-reaching. For one, the energetic processes during the merger can trigger significant changes in the galactic environment, such as the activation of quasar-like phenomena if the central black holes accrete material rapidly. Additionally, the mixing of different stellar populations and gas can lead to a more homogeneous galaxy in terms of its chemical composition and age distribution. Furthermore, galactic mergers play a crucial role in driving the overall evolution of the universe, building up the complex hierarchy of cosmic structures we observe today. They are not just spectacular events, they are fundamental processes that forge the galaxies and galaxy clusters that comprise the large-scale structure of the universe. Planetary systems face an uncertain yet fascinating journey when their host galaxies merge. The vastness of space plays a critical role in this process, as stars and their planetary systems are incredibly far apart relative to their sizes. When galaxies collide,
the chances of direct impact between individual stars or planetary systems are minuscule. This means most planetary systems survive the merger relatively unscathed, continuing their orbits around their home star as the galaxy's larger structures, like gas clouds, star clusters, and dark matter halos, undergo significant turbulence and reorganize. However, the gravitational interactions during a galactic merger can cause substantial shifts in the orbits of stars within the merging galaxy. These gravitational perturbations can lead to the ejection of some stars from their original positions, sometimes flinging entire star systems into the outer regions of the new merged galaxy, or even into the vast emptiness of intergalactic space. For planetary systems that remain bound to their parent stars, these shifts can alter their paths around the galactic center, potentially moving them into different environments with varying radiation levels, densities of interstellar medium, and tidal forces. Moreover, the increased star formation triggered by the merger can lead to nearby supernovae, which may have profound effects on planetary systems. Intense radiation and shock waves from supernovae could strip planetary atmospheres or disrupt orbital stability, especially for planets orbiting closer to their stars. Despite these potential hazards, the overall number of planetary systems affected directly remains relatively low given the sheer scale and number of stars involved. Thus, while galaxy mergers are truly transformative on a cosmic scale, the microcosm of individual planetary systems tends to endure, riding the waves of these vast interstellar events. The alignment of galaxies over vast distances is a surprising and intriguing phenomenon that hints at the interconnected nature of the universe's large-scale structure. Galaxies are not randomly scattered, but instead appear to be aligned along large filamentary structures in a pattern known as the cosmic web. This web is composed of immense filaments of dark matter and gas, stretching across hundreds of millions of light-years and connecting clusters and superclusters of galaxies. The underlying cause of these alignments can be traced back to the initial conditions of the universe and the influence of dark matter. In the early universe, small fluctuations in the density of matter created slight overdensities and underdensities after the Big Bang. Gravity caused the overdense regions to attract more matter, gradually growing into the large-scale structures we see today. Dark matter, which makes up about 85% of the universe's total mass, plays a crucial role in this process. It does not interact with light, but exerts a gravitational force that influences the distribution and movement of galaxies. As dark matter forms these elongated filaments and nodes, galaxies forming within these structures naturally align along the filaments due to the gravitational pull and the flow of matter. Furthermore, the rotational axes of galaxies can become aligned with these filaments as a result of angular momentum conservation during their formation within the cosmic web. This alignment phenomenon extends over vast distances, with studies showing correlations in the orientation of galaxies separated by hundreds of millions of light-years. These cosmic alignments provide a window into the underlying dark matter framework of the universe and offer valuable insights into the initial conditions that have shaped the large-scale structure since the early moments after the Big Bang.
As we continue to study comets and their organic compositions, each new finding brings us one step closer to unraveling the grand question of how life began and whether we are alone in the universe. The next wave of space exploration missions promises to push the boundaries of our knowledge and unveil new aspects of our universe, targeting a range of intriguing objectives. One of the most anticipated missions is NASA's Artemis program, which aims to return humans to the moon by the mid-2020s, establishing a sustainable presence on the lunar surface. This mission is not just about revisiting our celestial neighbor, but also about setting the stage for future crewed missions to Mars. Artemis will enable scientists to study the moon's resources in greater detail, particularly water ice at the lunar poles, which could be vital for sustaining long-term human exploration and developing in-situ resource utilization technologies. Meanwhile, enhancing our understanding of Mars continues to be a priority, with NASA's Perseverance rover already exploring the Martian surface, collecting samples that will be returned to Earth by the Mars Sample Return mission in the early. These samples are expected to provide unprecedented insights into the planet's geology and potential past habitability. Additionally, ESA and Roscosmos are collaborating on the ExoMars program, which includes the Rosalind Franklin rover, designed to drill below the Martian surface in search of biosignatures. In the realm of outer solar system exploration,
NASA's Europa Clipper mission, slated for the 2020s, will conduct detailed reconnaissance of Jupiter's moon Europa, investigating its subsurface ocean and its potential for supporting life. Another exciting mission is the James Webb Space Telescope, JWST, which has already begun its journey to explore distant exoplanets, the early universe, and the formation of stars and galaxies with unprecedented clarity. JWST will look for atmospheres around exoplanets, potentially identifying planets with conditions suitable for life. Finally, the field of planetary defense is also witnessing advancements with NASA's DART mission, Double Asteroid Ray Direction Test, a kinetic impactor technique to test our capability to deflect a potentially hazardous asteroid. Collectively, these missions herald a new era of exploration, bringing us closer to answering fundamental questions about our place in the universe, the potential for life elsewhere, and the continued survival of humanity. Space telescopes serve as our windows to the universe, providing clear, unimpeded views of celestial phenomena that ground-based observatories can't achieve due to Earth's atmospheric interference. This unhindered perspective has fundamentally transformed our understanding of the cosmos across diverse wavelengths, from visible light to infrared and beyond. The Hubble Space Telescope, orbiting above our planet since 1990, has become iconic for its stunning imagery and rich scientific contribution. Hubble has allowed astronomers to measure the rate of cosmic expansion with unprecedented precision, lending support to the theory of dark energy, a mysterious force accelerating the expansion of the universe. Additionally, it has captured detailed images of distant galaxies, star-forming regions, and exoplanets, significantly advancing our knowledge about the structure and evolution of the cosmos. Beyond optical observations, space telescopes like the Chandra X-ray Observatory and the Spitzer Space Telescope have delved into the high-energy and infrared realms respectively, providing insights into phenomena inaccessible to visible light instruments. Chandra's X-ray observations have unveiled the violent behaviors of black holes, neutron stars, and supernova remnants, revealing the extreme conditions that shape these exotic objects. Meanwhile, Spitzer's infrared capabilities enabled the study of the early universe, star birth, and planetary formation processes cloaked in dust that blocks visible light. With the recent launch of the James Webb Space Telescope, JWST, astronomers are poised to delve even deeper. JWST is designed to peer back in time to the first galaxies formed after the Big Bang, and to meticulously study the atmospheric compositions of exoplanets, potentially identifying biosignatures. Each of these instruments expands the frontiers of our understanding, providing piecemeal insights that together weave a comprehensive tapestry of the universe, its origins, and its inexorable evolution. Human space travel beyond the moon presents a tapestry of formidable challenges, both technical and physiological, each demanding innovative solutions. One of the most daunting obstacles is the extended duration of missions to destinations like Mars, which could take 6 to 9 months one way, followed by an extended stay to align with optimal return window. This duration significantly increases exposure to space radiation, including galactic cosmic rays and solar particle events. Unlike the relatively short journeys to the moon, astronauts on Mars missions would not benefit from Earth's protective magnetosphere, making advanced radiation shielding and potential pharmaceutical countermeasures a critical area. Another major challenge is the psychological and physical toll of prolonged weightlessness. Extended periods in microgravity can lead to muscle atrophy, bone density loss, and fluid redistribution, which affects vision and other bodily function. While the International Space Station, ISS, has provided valuable data on mitigating these effects through exercise regimens and medical monitoring, the time frame for Mars missions will test these countermeasures to their limits. Additionally, the psychological impacts of isolation and confinement in a spacecraft for months on end, compounded by the communication delays with Earth that can stretch up to 20 minutes, require robust mental health support systems and well-designed habitats that offer some degree of privacy and comfort. Logistics and life support systems also pose considerable hurdles. The need for sustainable life support systems that can recycle air, water, and waste efficiently for extended periods is paramount. These systems must be extraordinarily reliable, with redundancies built in to mitigate failures far from home. Moreover, carrying enough food and supplies for long-duration missions or developing technologies such as hydroponics or bioregenerative life support systems to produce fresh food in space are critical areas of development. Finally, propulsion and energy are significant challenges. Current rocket technology, while advanced, still requires months to traverse the distance to Mars. Nuclear thermal propulsion or advanced ion propulsion systems are among the options being explored to reduce travel time and improve mission feasibility. Human space travel beyond the Moon will require a confluence of technological ingenuity, rigorous testing, and international cooperation to surmount these challenges and realize the dream of interplanetary exploration. As humanity prepares to venture deep into the cosmos, a suite of innovative technologies is being developed to meet the unique demands of deep space exploration. One of the forefronts of this advancement is propulsion technology. Traditional chemical propulsion, while vital, is not efficient enough for long-duration missions to destinations like Mars and beyond. Researchers are thus investing in nuclear thermal propulsion, (NTP), and nuclear electric propulsion. NTP involves heating a propellant, such as hydrogen, with a nuclear reactor, providing a higher thrust-to-weight ratio than conventional systems. NTP, on the other hand, utilizes nuclear energy to produce electricity that powers ion thrusters, offering high efficiency and extended operational capabilities that could significantly reduce travel time. Future space missions are poised to revolutionize our understanding of the cosmos by addressing some of the most profound questions about the universe's origins, structure, and potential for life. These missions can provide critical insight into the conditions that could support life. This observational puzzle led to the theorization of a mysterious force termed dark energy, which now constitutes about 70% of the universe's total energy density. Dark energy acts as a repulsive force, counteracting the gravitational pull of matter and thereby driving the accelerated expansion. The exact nature of dark energy remains one of the biggest mysteries in cosmology. It seemingly behaves like a cosmological constant, a term Einstein once introduced and later discarded, representing a uniform energy inherent to the fabric of space itself. However, some theories suggest that dark energy could be a dynamic field evolving over time. Quantum mechanics and general relativity, the pillars of modern physics, struggle to coherently explain this force within a single framework. Researchers are probing deeper with advanced telescopes and instruments, hoping to unlock the secrets of this enigmatic energy. The accelerating expansion hints at a universe heading toward a cold, diffuse future, a profound shift in our understanding of cosmic destiny. To grasp the influence of black holes on the universe's structure, picture these enigmatic entities as cosmic sculptors, shaping their surroundings through gravitational mastery. Black holes, despite their name, are anything but empty voids. Formed from the remnants of massive stars, they possess gravitational fields so intense that not even light can escape. At the centers of most galaxies, including our own Milky Way, lie supermassive black holes with masses equivalent to millions or even billions of suns. These galactic giants exert profound effects on their host galaxies, anchoring them gravitationally and regulating star formation through their powerful accretion processes and jet outflow. When matter spirals into a black hole's accretion disk, it heats up and emits intense radiation, triggering energetic phenomena that can influence entire galaxies. These high-energy jets can expel vast amounts of gas into intergalactic space, affecting the rate at which new stars are born. Imagine these jets as cosmic gardeners, pruning and shaping the galactic landscape. Moreover, black hole mergers, detectable through gravitational waves, contribute to the dynamic evolution of galaxies, sometimes causing dramatic rearrangements of stars and altering cosmic structure. The dance of black holes and their gravitational machinations thus plays a critical role in the grand architecture of the universe, sculpting everything from the distribution of galaxies to the intricate web of the cosmic fabric itself. Magnetic fields play a crucial yet intricate role in the life cycle of stars, acting like invisible threads weaving through the tapestry of star formation. In the cold, dense regions of molecular clouds where stars are born, magnetic fields exert significant influence over the gas and dust collapsing under gravity to form new stars. Imagine a cloud of gas being squeezed into shape by a network of magnetic ropes. These fields provide a counterbalance to gravitational forces, slowing down the collapse process. This delicate tension allows the gas to cool and condense more gradually, fostering the formation of a dense core that will eventually ignite into a star. Furthermore, magnetic fields contribute to the angular momentum problem in star formation. As gas and dust collapse to form a new star, they begin to spin faster, much like a figure skater pulling in their arm. Without a mechanism to shed this angular momentum, the material would be flung out, preventing the formation of a stable star. Magnetic fields help redistribute this momentum by channeling some of the energy away through outflows and jets, effectively acting as a braking system. These outflows can sculpt the surrounding environment, clearing away excess material and influencing neighboring star formation sites. Thus, magnetic fields are not passive bystanders, but active and dynamic participants in the complex ballet of star creation. The phenomenon of irregular and fast rotations in some stars is a fascinating chapter in the cosmic storybook, driven by various dynamic processes and stellar interactions. On one hand, these rapid spins can be a relic of their origin. Stars begin their lives within the swirling confines of molecular clouds, and the conservation of angular momentum plays a crucial role as they collapse into denser forms. Much like an ice skater pulling in their arms to spin faster, a contracting star increases its rotational speed. Variations in the initial conditions of the molecular cloud, such as turbulence, magnetic fields, and the distribution of angular momentum, can lead to stars with inherently fast, irregular rotations. On the other hand, interactions during a star's lifetime can significantly alter its spin. For instance, star systems with close companions, such as in binary or multiple stellar systems, frequently exchange angular momentum through gravitational interaction. When two stars in a binary system are close enough, tidal forces come into play, rapidly spinning up one or both stars if mass transfer occurs. Furthermore, stellar mergers and close encounters can impart angular momentum to stars, rapidly increasing their rotation. Even isolated stars can experience rotation changes due to magnetic activity and stellar winds. These processes can lead to the loss or redistribution of angular momentum, sometimes resulting in irregular rotational velocity. In the grand cosmic dance, the factors contributing to a star's rotation are a blend of inherited traits and dynamic experience. In the grand tapestry of the cosmos, every force, from the enigmatic push of dark energy to the silent pull of magnetic fields, contributes to a universe in constant motion and transformation. The mysteries we face, be it the nature of dark energy, the gravitational choreography of black holes, or the rotational quirks of stars, are not just scientific puzzles, but windows into our origin and destiny. As we unravel these cosmic threads, we deepen our understanding, not only of how the universe works, but also of our place within it. The universe is not a static backdrop, but a dynamic, evolving entity, and humanity, in its quest to comprehend it, becomes a vital part of its ever-unfolding story.